All right, hi everyone. I'm Nathan Fulton. I'm a research scientist at IBM at our Cambridge office, which is just a couple blocks down the street. And Jake is a research engineer on my team. So we've been working on an open source library called Mellea for a thing we're calling generative programming. The way that I'm going to structure this session is I'm going to kind of give a mini lecture at the beginning explaining like the motivation for why we're building Mellea and what it's for. And then we'll go through a sequence of examples that are sort of like little miniature didactic applications that demonstrate some of the key concepts that we're trying to get across and that we've built Mellea to help enable. So before I get started with the sort of sermon version, portion of the talk, we have, so for all of the examples, so first of all, the talk is self-contained. So if you don't want to follow along in a notebook, you don't have to. You can just shut your notebook and listen. I'll have like condensed versions of the code on the slides. You can just like follow along. We'll explain it line by line. There's no need to follow along, but if you would like to, you can go to this Colab link or download the corresponding Jupyter notebook. And if you want to follow along, if you want to follow along in Colab, what you can do now is go there and just run that first cell. This will do sort of the setup phase. It'll download model weights for a couple of models. It'll install our library and do a few other setup steps. So after you click that, if you see something like this, that means the install is starting. So we've had some issues with Colab in the past. This can fail in one of two ways. So sometimes the Olama download fails. And in that case, you can just like refresh the page and try again. And the other thing that can happen is you'll see like some error, blah, 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 dtype, blah, blah, blah. Again, like refresh and run again. If both of those fail, then you can download the notebook and try, or you can just give up, close your notebook, and follow along. It's not necessary to have the tutorial running. Like I said, all the code will be on the slides as well. Oh, and by the way, the reason that Jake is here, he's gonna. So if you end up having issues at any point, first of all, you can just raise your hand and ask. If it's like specific to your environment, I'll just like float Jake around to you, and he can help you out, sort of as a sidebar thing. But if the question is not just pure technical, my environment's not working for whatever reason, if it's a more conceptual point, please like speak up and ask questions at any point during the talk. Cool. So okay. So like I said, I want to start with a little bit of motivation, and to motivate why we're building Mellea and what this generative programming thing is, I want to go back all the way to the beginning of time in AI, which for the current era is like 2017, right? So the way to think about this is that a lot of the sort of algorithmic challenges to natural language modeling and sequence modeling in general were starting to be solved. So some of the issues with early recurrent networks and LSTMs were being solved by transformer and other types of architectures, but of course famously transformers. And a few labs and other pieces start coming into place, right? So we have the data because of the internet and open crawls. We have the hardware because of gaming and Bitcoin mining. And so the pieces kind of fall into place and some labs start scaling up. And almost immediately, some of those models start being made available, either behind APIs or closed sort of previews, or eventually in open weights. And then immediately, right, the hacker community starts doing what it does, which is sort of build toys and examples and cool things that nobody has built before, right? So a few really early examples. So there was a really early one. I've tried looking. If you find references to this, let me know, because I keep looking for references. I distinctly remember it, like it's etched in my brain, but I can't actually find it. But there was this nice little AI dungeon game in like 2018, maybe, that like you would just like talk with the model. This was like one of these first cases where somebody took like a BERT-style model, or it might have even been a GPT, and just sort of started chatting with it, right? Treating it like a chatbot. So that was an early example. There were some early examples with GPT of like generating research papers in quotes, right? So basically, there's this programming language called LaTeX that math and math adjacent fields use to typeset their documents, their research papers, and somebody just like said, hey, look, these early transformer models, pre-trained, no tuning or anything, they can generate LaTeX if you start prompting them because there's a bunch of LaTeX in the training set, and then if you just like let that run forward, then you'll get some like valid LaTeX that will like compile, and when you compile it, you get a PDF, and the PDF has like math equations in it and some text next to the math equations, and it's all, of course, complete gibberish. But it looks like superficially, if you don't know the math or you cross your eyes and let your vision go out of focus, then this like kind of looks like research grade mathematics. And then, of course, the immediate like analogy to that is generating code, which people started doing very, very early on. And it took a couple of years, but these turned into products, right? These early sort of toy examples, demonstrations of potential. So these like AutoGen style things eventually got instantiated in Copilot style products. And then, of course, the AI Dungeon thing, the chat with the model thing, sort of exploded onto the scene with ChatGPT, and then of course a whole diaspora of chat style products. And we're sort of living in that era. And there have been a few iterations of this, right? So this isn't like a one-off thing that happened. This is a cycle that happens every couple of years in this field. Some more examples. So React prompting and chain of thought, sort of the beginning of agentic style stuff, right? Along with tool calling. Again, there's this sort of primordial example from that same era, maybe a year earlier, where a team used basically took natural language, translated it into Mathematica, a natural language query about its system of differential equations, like give me the solution, right? And then translated that into Mathematica, ran dsolve in Mathematica, got the solution back out, and then translated that into natural language. Now we think of that as like an extremely pedestrian, I called a tool style use case, right? But at the time, actually, the paper was a little bit controversial because it was like cheating because the neural network didn't really solve the ODEs. It just generated the code to solve the ODE. And so this is an interesting case where sort of, the seeds of things, basically React prompting plus that is an agent, right? And the seeds of that, the implications weren't necessarily realized. And then reasoning models, right? So you can go back to like the FAIR Facebook AI Research Labs diplomacy playing bot, which was again one of these like really early GPT style things, and that eventually became what we now think of as reasoning models, or like things that generate think tags. So why am I telling you all of this? The reason I'm telling you all of this is because like these are toys, right? These are demonstrations of potential, like very powerful because they like show you what could be possible. And then the stuff over on the other side, those are products. And that 2-3 year gap is there for a reason. Getting from something like this to an actual product, an actual deployment that does something useful for people is an enormous amount of hard work. And that's the hard work that's being done in the agent space right now, we think. And a general observation that we've had from doing like sort of software archaeology with agent teams, both internally and open source and at clients, is basically, historically the way we thought about this was that solving natural language tasks with code is hard, right? So like classical NLP pre-LLMs, doing stuff with natural language is hard, right? And then the LLMs came along, and we sort of made the wrong, we made a wrong turn, right? We made like a really hard left turn that was a wrong one, which is why don't we start writing all of our code in natural language, right? And call it prompting. Whereas what we should have done is said, if we have natural language tasks, we have these amazingly powerful language models that can be used to solve those natural language tasks. They can handle the infinite variety of ambiguity and context that comes with using a language that is designed and used by, evolved from use by humans. But like not everything is a natural language task, right? If you need to do a set of things sequentially and it's the same set of things every time, that's code and it should stay code, right? So when we look at sort of cases where agent developments and deployments fail, it's usually because the wrong thing is being done with the natural language that's being used to program the system as opposed to being used in the appropriate place inside of a system. And that's not the fault of the people doing the development. We think that we have the wrong set of tools for building agents. The tools that we have today for building agents are fantastic for this sort of proof of concept toy thing, right? That's sort of the world in which they were built. And they're great for that, right? They're great when you have a small team size, one or maybe a few people, where the system is correspondingly small, right? You have like a prompt, maybe a couple dozen prompts. They're not like huge. And you have like some tools, not too many. Filling the arguments for those tools is not like super complicated. And the stakes are low, and the autonomy model is like, I don't know, a person's using it, it's going to fail, who cares, right? And if you want to go from a proof of concept to a productive deployment, historically, a few things happen, right? And we can see these happening. We can see these happening in the sort of timeline that I gave earlier. So the first thing that happens is that the team size grows, right? If you think about the Copilot example, right, you need to grab a lot more code data. You need to clean it up. Like the fact that it's Python, you know, like intermingling your Python 2 and your Python 3 can like really degrade the performance of a small code model. So there's this infinite variation of sort of ways in which you have to clean and tag and the pre-training and tuning data. You then maybe have to actually do the training differently, not just because you've cleaned up the data, but also because the sort of modality of the application has changed, right? So with code, sort of figuring out that we could do fill in the middle and not lose performance of, you know, doing left to right, that is a good example of how the training can change. The whole inference stack needs to be considered, right? So there is stuff like, how do I do KV caching? How do I do context management? How does all of the stuff that's happening with the language model interact with the rest of the software stack and the rest of the system? And of course, there's middleware. There's building the application itself, the product design stuff, doing integrations. And so anyways, the system grows, right? You have a larger team or many teams. The size of the code base grows. The complexity, you know, maybe even you're changing the model itself. And the reason for this, the reason that the team size and the system size is growing, is because the stakes have changed. You're not building a toy. You're trying to like have some impact on some core business process. And typically what comes with that is that the autonomy model changes, right? Maybe you want a full closed loop system, but at the very least, if what you're doing is relevant to something that you care about, right, then even with a human in the loop, you care about the fault model, right? You care about like how I handle things when they go wrong. How do I hand back control to the user, or how do I handle exceptional case management? So the way that we think about agent frameworks as they exist today is they're fantastic tools for building these sort of like demonstrations of potential. And on top of them has been built all of this infrastructure that lets you deploy those things. But at the end of the day, what you're doing is like you're deploying your MVP, you know, you're deploying your prototype, you're deploying your demo. And so they're sort of production-ready stacks in the sense that you can like deploy them to a ton of users, but not production-ready in the sense that like they do what you need them to do. You know, you build a system that does what it needs to do in production. And this is why you get all these think pieces about why using these libraries is horrible. It's why you see all of these reports from business schools about most agentic pilots failing and so on. So about a year ago, we set out to answer this question: how do we get from agentic, sort of what we call demo soup, and I'll get to what I mean by that in a second. So how do we get from this sort of demo soup thing to actually robust software systems that we can have some confidence in deploying? And the way that we started answering that question was by just doing some software archaeology. So looking at a bunch of agents, things that worked well, things that didn't, and trying to glean from those lessons that we could then codify in an application framework. So what we noticed was that most of today's agents are really just glorified prompts, right? It's mostly prompting and tool use. And the tool use and the prompting are closely related, right? The quality of the tool descriptions matters. And there are a few implications of this. So one is there's a huge issue with maintainability. So if you go grab the git commit history of one of these agent development life cycles, what you'll see is like a lot of tweaking of the prompt. And a lot of the tweaking of the prompt is happening with respect to like a very specific model, right? Like not just a specific model family, but like a specific point release, maybe a specific tune of that specific point release. And you see all sorts of weird, like change the type of quotes that I'm using, put this in capitals, don't put that in capitals, shift around the paragraphs, stuff like this. This is like one example of the sort of stuff that you'll see. And in here you can see there's like some stuff that's clearly exceptional case handling because of something that they saw that the model was doing that they didn't like. And then you, and this is a maintainability nightmare, right? Both because you accumulate these huge prompt essays that are responsive to little examples of the system misbehaving that maybe aren't even clearly documented, but also because like you move to a new model. You move to a different point release. You move to a quantized model. For any variety of reasons, you move away from that one specific thing you've sort of handcrafted a prompt for, and the system performance can degrade pretty substantially very quickly. A second issue is security. So I won't harp on this, but just suffice it to say, first of all, this is insane, right? Things like do not hallucinate with a capital N-O-T. My career depends on it, right? This is not engineering in any proper sense of the word. But it's not just that you're doing security by prayer. It's more serious than that because you're putting all of these like security constraints in a prompt. And what else are you putting in the prompt, right? Input from the user. And I thought that's a lesson that we had all learned from the web dev days, right? So like SQL injections aren't really that common anymore. We figured out like don't put user data into code. Cross-site scripting, I guess it's like a little bit more subtle, but like web frameworks today are pretty good at like getting you to mostly do the right thing. Like I don't know, you have to like almost try to like introduce a SQL vulnerability if you're like on the happy path of a web development framework today. But if you use any of these agentic frameworks, any framework that's designed for building applications with LLMs, you're not just encouraged, but almost forced to commingle user instructions and system instructions. So that's an issue. A third issue is efficiency. So again, you have two leverage points: the prompt and the tools, and the tools in the prompt are commingled, right? If you change a tool, if you add a tool, you need a description that goes into the prompt. And so as a result, a feature request comes in, what's your leverage point? The prompt, right? A bug report comes in, what's your leverage point? The prompt, right? And you saw some of that happening in the previous examples, in this particular example, but it happens basically everywhere. And it turns out that natural language like English is just not a good programming language for all sorts of super fundamental reasons. And they all show up when you accumulate these essay prompts, right? You have a bunch of different people editing various portions of the essay. The control flow is intermingled all over the place. There's no structure, or you have to really fight to maintain the structure because you don't have a notion of like lexical scope or information hiding. It's just English sitting in a text file. And by the way, this is an efficiency issue for two reasons. So there's the efficiency of the development life cycle, which I've been talking about. But there's also, like, when you grow these prompts, right, and they get really big and they get really complex, you need a very, very good model to be able to follow all of that logic. And so you need a big frontier model, and so your inference costs are going to be correspondingly huge, right? That's like assuming that you can get a model to follow the prompt in the first place. Often these prompts just grow to a point where the complexity of the system collapses on itself, either because the model can't follow the English language description of this complex thing that you've described, or maybe more commonly because, like, if you and I've done this exercise a few times, you take the prompt, you take all of the text files, all the prompts, you take it all away, you just like put that in a file, and then you take the input that the developer has identified as being like an evaluation item that the system can't handle. And you just provide the developer, you say, like, here's your prompt, right? Here's like the text you're showing the model, and here's the input that you are providing. Like, forget that there's an LLM, right? You follow the instructions in your own prompt for this input and tell me what's supposed to happen. And like, shockingly often these prompts get complex enough that like, if you step back and you forget all of the history of you developing that prompt or like your own internal mental model, if you step aside from all of that and you just look at the prompt and the input, even you can't tell like, oh yeah, the prompt isn't actually saying what you're supposed to do, right? It's hard to read off from a 10,000 word essay what you're supposed to do with a particular piece of input. Okay, so like uncontroversial observation, all of this stuff, agent development, inference scaling, et cetera, like these are obviously just programs. But this isn't like this observation I think is one that anybody who has done any amount of software engineering is like, yeah, of course, right. When you build an agent is a program. But it's something that we want to take a little bit more seriously than the sort of like surface level observation. These agent frameworks, the agent style of software development that I've been talking about, it's a fantastic tool, again, for demos for what in the 1970s they called programming in the small, building small-scale systems with small teams that do small things. And then when you take a tool that's designed for building small-scale systems with small tools doing small things and try to use that same sort of system, that same set of abstractions to build a large system with a large team doing larger things, like bad things often happen. And this isn't a new observation, right? So if you go back all the way to the beginning of software engineering, and this is a paper from the 1970s, the title of which is Programming in the Large versus Programming in the Small. And like you could basically take this paper, replace the examples that they're using with examples from agent development, and it like has aged perfectly. And basically what they're saying is when you take frameworks that are designed for doing small scale things and then you try to build large scale things, like your tools are wrong and you end up like obscuring all, like you learn all of this stuff about the world, about the thing that you want to automate, and then you throw it all away because you're like shoving it into the wrong abstraction, right? They call it an exercise in obscuration is their fancy way of saying what's going on. But like they wrote a paper about all the problems with agent development, but in the 1970s. Okay, so we're building a library called Mellea that's designed to sort of encourage a different type of agent development. It sits here in the stack, so you can think of this as being a library for writing applications that use large language models. But one of the things that we've done, and I should mention, by the way, so we sit in the Cambridge Research Lab for IBM. Right across from us in the next aisle is the team that pre-trains our Granite series of foundation models. So one of the things that we've been very careful to do is to build the right tendrils into the architecture of Mellea such that we can sort of reach down into the runtime system and even into the model weights themselves, such that when a new model feature is developed or new inference technology is developed, we're able to surface that. Right, so these models will continue to develop, right? Like the set of features in these models will continue to grow. When that happens, you need to modify the runtime, and we've sort of built, we've built hooks into the right parts. We hope the right parts of Mellea's architecture such that as new features get added to models, we can sort of surface nice application layer abstractions such that the end developer can use that feature without having to like intimately know how it works within the model, which is important both because like abstraction boundaries are good, not having to understand every aspect of every stack, every portion of the stack is like these are good things we know, but also because if you get that separation right, you become much less dependent on like one model. You can develop against a model that supports the following features and not a particular model, right? So we've built a bunch of applications in Mellea, both sort of greenfield and also taking existing agents and rewriting them in Mellea. And basically what happens is you go from this like prompt engineering with tools exercise to a very different style of programming where you're typically issuing like these fairly small imperative instructions. You're circumscribing those instructions with various precondition and postcondition checks. And you're using sampling strategies to ensure that those requirements are satisfied. And then because of this, you can build abstraction boundaries around places that you're using your LLM. And then that gives you a mechanism for more safely and composing pieces of a system. We've done some internal rewrites. So these are each of these graphs are showing the development of an agent with Mellea and then with just like classical agentic style prompting and tool use. The pink are Llama 70B, and the blue are one of IBM's much smaller granite models. So this is an 8B parameter model, so you can like run on your, if you have a MacBook, even like an M1, you can run these blue models. The pink ones are 7dB models, so definitely not local. So a couple of things, right? We just did a straightforward port of that prompt into a sort of Mellea program. So there was nothing, like there was no like sophisticated engineering happening here, right? It was mostly just a port. So a couple of things. You'll notice that even on the large models, we get a performance gain, right? The other thing that you'll notice is that on the small models, we get a much larger performance gain. In both cases, actually, where the Mellea version of the agent outperforms, in the small model, outperforms the agentic version in the large model. But the other, maybe most important thing from these two case studies is this left chart, where this is a prompt that was developed really closely against the Llama 7dB model, right? So that was like the version of the model that the development was happening on. And then you want to take that workload on a 7dB model and lift and shift it back to a much smaller model. There are many reasons why you might want to do this, right? Maybe you want to start doing inference scaling with that workload, so that you can do like best of X sampling where X is large, or just like you're sensitive to cost because you want to scale that thing up and start running it on like every single commit that's made to a repo by a large team, right? So there are all sorts of reasons why you'd want to lift and shift to a much smaller model. When you do that for this database agent, you go from like 78% on this benchmark to just like the smaller model just doesn't work at all with the original prompt. But if you rewrite that agent in Mellea first, and you see this performance boost with the 7dB model, and then you just take that exact same program and you change the model ID, right? The 8B model like does fairly well. These are two case studies. They're anecdotes, but this is like pretty common, right? When we write programs in Mellea, we can often write them against a frontier model and then just take that and run, a small Granite 8B or 3B model or GPT OSS, things that like run on your laptop, and we'll see like minimal performance degradation, which is pretty cool because it lets you scale, and when you can scale, you can do things that are different in kind. Okay, so that's the end of the sermon. I'll stop here for two reasons. First, just give people a chance to react, tell me I'm wrong, ask questions, agree, any of the above. And then second, for anybody who's following along, if you desperately want to follow along and that first install step didn't work, raise your hand and Jake can come around and help debug. Okay, either nobody's following along or we got really lucky. All right. All right. So now I'm just going to go through a series of examples. Each of these examples are didactic, meaning they're like small, simple examples that we've extracted from much larger instances of these sorts of things happening, and they're designed to illustrate some core principle, right? So I'm going to start with a hello world example, just to like sort of give you some anatomy of what a Mellea program looks like. So this is hello world, right? We're just sort of spinning up an LLM and asking some question in a chat context. The first thing that we do is we say start session. So Mellea has backends, which you can think of it as being a combination of the inference provider that you're using. So this could be Llama, it could be an OpenAI compatible backend, it could be a model that you're running on transformers locally. And then in addition to the backend, there's also a context. And you can think of and contexts are immutable, and you can just think of a session as a sort of convenience utility that just manages a mutable ref to your context. So as you're doing things, right, you pass a context in, you generate on that context, you get a new context, and the session just holds a mutable ref to the latest context, right? The context at the end of the latest call. So there are different, right now there are two types of context. There's a simple context, which is just does not preserve any history, right? So every call is happening on a context that is constructed for that particular call. You're not using the chat context. You're not using the chat history to construct your context. You're sort of on each inference request putting the things into context that you want for that particular request and not relying on a trajectory of chat messages. That's what we sort of find works, like engineering systems like that and just using the lexical scoping of your programming language tends to be the result in more robust systems. But sometimes you do actually want to have that like chat trajectory, right? Usually when like there actually is a chat happening with the user. And so there's also this thing we call a linear context, which you can just think of as being a user assistant style chat history. You can also implement your own contexts, right? So it's a fairly simple interface. And you know, if you're familiar with what SGLang does with KV cache management, you can sort of foreshadow some of the stuff that we're working on in that portion of a session. And then the other portion of a session is the backend, which I've already sort of explained. Okay, so we initialize a session, and then we send a chat message into that session. So we say, tell me some fun historical facts about something. And then that's a blocking call. This session has these methods on it. Each of these methods is really just constructing a thing we call a component and then passing that into the backend's act function. By default, our implementations are blocking calls, but you can put an A on the front of any of these methods, and you'll get an async version. The output from that call answer has type model output thunk, right? So in this example, because we made the synchronous call, that thunk will immediately be computed, and then you can access the value. You can access the value of that immediately. Otherwise, if you call the async version, that thunk may or may not be computed, and at the point where you want to use it, you'll have to wait on it, and that could trigger a sequence of computations. Right? The name is suggestive if you're familiar with lazy functional programming, right? It's called the thunk for a reason. It's a thing that represents a computation that you're sort of building up and you're going to then execute. Okay, and then we print the output of the message content. So again, nothing exotic happening here, right? This is just a hello world example. If you read this code and sort of imagine that it's doing what it reads, then your intuition about the input and output behavior of this program will be correct. Okay, so let's look at one of the simplest and most fundamental design patterns in applications that we write in Mellea. It's called instruct, validate, repair. It's important enough that we've made one of these sort of top-level session methods to support it. So the first thing that we do is just issue a simple imperative instruction. One of the things that we do in Mellea is when we have a big prompt that says like do this and then do that and then do that and then do that, you know, we don't put that like control flow into the prompt. We just break all of that control flow out and then we make each of those an individual call. This has a few advantages. So one is that it tends to be more robust, tends to be more transferable. You can engineer the context for each specific call, right? So that at that particular point, you're providing the model with exactly what's needed for that portion of the process. And the other advantage is that the calls tend to be smaller. And so you're making more calls, but each of those calls is smaller, which turns out to have some efficiency advantages because the cost of output tokens is quadratic in the length of the input. And so if you make a bunch of small calls and you're able to do with an equivalent number of tokens with a sequence of smaller calls what you could have done with one large call of the same size, you're actually getting some pretty significant performance advantages there because of the asymptotic nature of token generation in classical transformers. Okay, so another argument that you can pass into this instruct thing is requirements, which is takes a list of requirements that should be true of the output of the instruct call. And those requirements are used in two ways. So we pass them in at generation. So this instruct thing creates a component in Mellea called the instruction component. it corresponds to, there's a Jinja template that tells you what that thing gets represented as. You can define one of those for each particular model family. You can go in and you can tune a model against that specific format if you would like. You can do prompt optimization on that template, et cetera, right? But it's fairly pedestrian. Like all it is the instruction, and then make sure you follow these requirements. So it's used at generation. It's also used at validation. So after generating, we take the output and we then check that the requirement passes. That check can happen in a number of ways. So by default, just as like a way of allowing you to get started, easy to use, the requirement, natural language requirement, can just be checked with LLM as a judge. So you just take the output and you ask the model again, hey, you gave me this output. I want this to be true. Is it? Right? So no guarantee that the LLM doesn't just hallucinate an incorrect answer to that, just like it hallucinated the incorrect result in the first place. But the other thing that you can do is you can specify validation logic that is just code, right? So in this case, we have a requirement that says use only lowercase letters. So you can define a validation function that just checks that the lower of the output is equal to the output. Right, this sort of post-condition checking, it's a very natural thing to do. Most of the things that we do in Mellea, that we've added to Mellea, we're just putting standard interfaces around things that we were all already doing in our own code, and we just didn't have a common language for. And that common language is important, right? Because if I write a large library of validation checks against an interface that I find sensible, and then you're using a different interface, you've got like this end-to-end problem. The other thing you'll notice here is that these two say rec and this one says check. So the reason that it says check is just, especially with smaller models, but even with large models, it's sometimes useful to say I want to check a requirement after generation, but not actually included in the prompt. So the canonical example of this is do not mention purple elephants. And like not to anthropomorphize too much, but like who here is thinking of a purple elephant right now? Right. So it can be you can sometimes get substantially better performance by enforcing a requirement post hoc, but not mentioning that requirement in the generation phase. Okay, so you can pass this set of requirements into an instruction. And then the other thing you can do is you can provide a strategy, and this is another place where having a common language, a common set of interfaces, and object protocols is useful, because we can say, here we're saying do rejection sampling, so just like if the requirements aren't satisfied, sample again, with a specified loop budget. And this is nice for a few reasons. So first of all, that's with a loop budget of 5 or any finite loop budget, right? This is no longer a program with a loop, right? This is a program that we can like unwind, right? We can unwind that loop. We can schedule a computation. Yeah.
Sorry, can I ask a question about the requirements and the checks? Is it that the requirements are part of the system prompt and the checks are like another call to the LLM? Or?
Yeah. So for all of these, so this instruct call will result in 3 invocations of the LLM. There's one for the instruction itself, which contains the instruction and the set of requirements. There's one for these two. There's one after that to check the output with respect to these 2 requirements. So that's 3. And then this one, because you've provided validation function, there's no LLM called. Okay. Right. So this sampling strategy thing in its abstract type, in its interface, it knows about the requirement type, and so you can implement your own sampling strategies. Mellea ships with a sort of a library of various inference time scaling techniques that are implemented according to the strategy interface, and we've got a whole research team at our Yorktown lab that's sort of working on implementing all sorts of inference time scaling stuff. In that strategy thing, and we're also implementing, it's also a fairly common thing for us to implement like domain-specific sampling strategies when we're working on particular types of agents. All right. So if we take the thing that we just saw, and then we can wrap it in a function, right? So we we take in the name and the notes, and then we generate the email, and then we know now that this LLM call has like a type signature, but more than that, it also has a set of semantic invariants on the output, right? Because we know that each of those requirements is at least valid. At least the LLM thinks that those things are true, right? And if they were deterministic checks, we like know them to be true, right? And so we have invariants on the output of this, like this some semantic properties of this string that we know, like for example, it's all lowercase. So if you're following along, you'll probably see something like this. This was just one example. You see that we start sampling 5 times. We see that some of the requirements fail, and then eventually we see a success, and then we get an email that does indeed meet all of the requirements that we stated. Sometimes that happens immediately, right? So this is a stochastic thing. The other thing that you'll notice in this function is that there's an else branch. So if we succeed in sampling, then we can return the result. And then if not, if after 5 times we don't have a result, what do we do? And in this case, it's an email. I mean, what to do? So return the first example. Return the first result if none of them succeeded. But one of the pieces of feedback we get from folks who are developing agents with Mellea or developing code with Mellea is that they like. One of the things that they say that they really like about it is that it puts them back in control. When they're developing agents, they really feel like they're being dragged along by their model. And then when they start writing code and writing their agents in a sort of more Mellaic style, they feel like they're much more in control. And so here, for example, right, you might return an exception. You might trigger another workflow that's designed specifically for that case. You might like escalate this to a human or any number of things. Okay, I'll stop here for 1 second before moving to the next example. Any questions so far? Cool. I want to mention one more time, right? All of the examples in this, these are all didactic, right? They're all like, right? We have an hour, so we try to take like things that we see are useful over and over again and provide you with really simple examples of those. But this instruct, validate, repair thing, in Mellea we provide a bunch of batteries included stuff, right? So there's a nice interface for requirements. There's a bunch. We're building out a standard library of requirements for various domains, finance, legal, etc. And the sampling strategies, right? We have implementations of. Right, you can do this sort of thing in your own without using Mellea as well, right? Yeah.
I assume this is the case, but and I haven't looked at the repo yet. But do you also, in the batteries included thing, have like examples of code generation with Mellea and like kind of like how you do the same thing in IVR with that?
Code generation.
Like for example, if you give it a task and then to validate that it executes correctly, and so on through the.
Yeah. So there's a small library. I had an undergraduate intern last semester who started working on a library of Python sort of requirement checks and implemented all the integrations with various sandboxing techniques. Yeah, is that what you were asking?
Yeah, I'll take a look at that.
Right. Yeah, and that's something that we plan on like continuing to grow over time. Yeah. Cool.
I'm not sure if I have a similar kind of question. Were you looking for something that shows how you might have to do it without Mellea, or?
No, I was curious because like I've done something similar where your point about like everyone's having to do this sort of steps and implement themselves and like the retry loops and everything. Where I was doing like kind of code generation with Claude and then checking and executing it and making sure that it's matching against certain checks at the end, and I'm like, this sounds very useful. So I was just looking if there were some examples, and if it's like kind of like built-in support for things like that, very easy to do.
Yeah, there are certainly examples, and we're working on the built-in support thing. And if there are like specific things that you want, especially in that space, in the code execution space, like just feel free to just like open issues and tag them as like feature and just like say things you want, right? We're happy we're happy to engage with just, hey, this would wish list style stuff.
Going back to my question, do you have anything that would show like a comparison before and after Mellea?
So we do. I'll get to that later in the slides, actually.
Okay.
There's one of like a GPT researcher style thing. And the prompts that I was showing earlier, like the big prompts for maintainability and security, that was a GPT researcher prompt. And we have a Mellea implementation of that prompt.
Okay.
Okay. So another didactic example. The point of the following example is basically like when you do this instruct, validate, repair thing, what you get is an abstraction boundary, and then you can use that abstraction boundary in all sorts of nice ways. For this example, we need a little piece of syntax. This is just syntactic sugar, but it's a nice piece of syntactic sugar. You can import a decorator called Generative from Mellea, and then just like @generative on the top of a function. And what that does is it turns the function into a Mellea component, and then you can call that function, which is equivalent to like performing an action on this im right here as a Mellea session. So it's passing this function into this function stub into the model and saying basically like, give me the output of this function given the doc string and the input provided by the user, right? And so you can sort of like write something like a sentiment classifier function and use it like you would use a function. But underneath the hood, it's an LLM call. So I'm going to use this @generative syntax for the rest of this example. The point is, it's a nice piece of syntax, especially for describing this way of thinking. But you can also do this with instruct, validate, repair things. You can do it with any sort of Mellea program. So suppose that we have two libraries. Maybe these libraries are developed by different people on the same team, maybe by different teams, maybe by two separate organizations that have never heard about or know each other, right? Standard software engineering stuff. Somebody else is going to write code. I'm going to use it. I don't need to like talk to them to know how to use their code. So one of these libraries we'll call the summarizer library, and it's just a bunch of functions that like summarize things, right? Summarize meetings and contracts and short stories, and there are specific things that you want to get out of the summary that are described in these doc strings. And then there's a second library, again, just as a didactic example, right? We'll call it a decision aids library, so it can propose a business decision or a risk mitigation strategy or a novel recommendation. And again, the doc string and these have type signatures, so there are some inputs the user is supposed to provide. And there are doc strings sort of saying what the expected output is going to be, right? So there are a lot of ways in which these things obviously compose, right? So if you have a summarization of a meeting, it could be super reasonable to generate risk mitigation strategies based on the summary of the meeting. If you have a summary of a contract, it could be very reasonable to summarize a business decision or to recommend or propose a business decision based upon a summary of the contract. Should I sign the contract? What should I change about the contract? Or given a summary of a short story, it might be reasonable to get some recommendations of novels that you might enjoy if you enjoyed the plot or theme of that particular short story. It's not a one-to-one thing, right? So if you have a summary of a meeting, it could possibly be reasonable to propose a business decision, right? Should we purchase this product? Should we work with this team? Should we do prioritize feature A or feature B? And given a summary of a contract, it could be reasonable to generate risk mitigation proposals. So which clauses in this contract are ones that we should maybe pass off to our M&A team. But there are also ways in which these don't compose very well. So given a summary of a meeting, you probably almost never want to generate novel recommendations. I suppose like if you're at Enron in the late 90s, this could be an interesting thing to do, but generally this is not an interesting direction for this composition to go. And similarly, if you're not like bundling subprime mortgages, it's probably not going to be super reasonable to summarize a contract and then generate a novel recommendation based on that contract. And also like the on-to direction of this thing, right? So if I generate a risk mitigation proposal, that's not a meeting, so it doesn't make sense to try to summarize a meeting based on the output of that function. So one of the things that you often see in sort of React-style agents is that the trajectory, there's like this upper bound to the trajectories where the whole thing falls apart. 14 is often a magic number that people throw around, but like the particular number doesn't matter. The point is like it's small and falls apart at the place where you normally expect combinatorial blowup to fall apart. And the reason that's happening is that you're taking cross products of things that may or may not compose, right? So you can address this, and if you have a React style agent and you want to do the React style thing, like open domain, let it try all the things, but you want to address that issue with the trajectories sort of falling apart at the place where an exponential typically does. What you can do is introduce these compositionality checks. So for example, we can introduce a check that says that just checks whether or not some piece of text contains an actionable risk, right? And then we can use that composition check. By the way, the return types of each of these functions like entail constrained decoding. So here we're going to get a yes or a no, and so we can use the output of that in a programmatic way. I'm going to take my name tag off because it's jiggling against the mic. Okay, right. So and then you can use those compositionality checks in your outer loop, right? So you can say go through each individual function, and you can say you can say I now have some output from one, and I want to check if that output contains an actionable risk, and if it does, generate a mitigation, and otherwise like don't do that step, right? You can also do this offline, right? So if you have a whole bunch of stuff and you want to know how it composes, you can like ask a priori, right? Do these things compose? And then that gives you a sort of constrained automata that you're then exploring at runtime. All right, so that's the end of that example. Again, it's very high level, very didactic, just meant to demonstrate a thing that we've seen be useful in practice, which is just that when you wrap your when you wrap your LLM, when you make your LLM call small and self-contained as possible, doing one thing and doing it well, wrapping it in requirements where that makes sense, and then introduce compositionality checks, you can push these trajectories of agents far further than they would go if you just allow anything to happen after anything else. Any questions about this example? Great. So IBM has another sort of series of models and associated software called Dockling. So Dockling is just, you can think of it as like OCR really on steroids. But for the purposes of this talk, throw in a PDF or an image or anything, get back some like structured XML style thing, like a tree that you can, like a parsed document, right? So for example, we can pass a PDF in and we can say get the first table, and then we can run a Mellea program that says add, grab the feature row and add a new column, and in that column give the name of the model that was discussed in the feature row of that table. So this is what that code looks like. We have a Mellea component called a rich document. The sort of purpose of showing this Mellea Dockling example is that so far we've seen components that are very simple, basically prompt templates, things like an instruction or a generative slot. Rich document is an example of a component that actually has a lot of internal structure, right? And a lot of like semantics associated with that internal structure. So we can get a rich document, and then we can run this im.transform function, which can take that table and then execute a natural language query against that table. You can think of this as basically like running it's running a method where that method happens to be a natural language instruction, right? You're just running a method on table one. This is a more general thing that you can do with Mellea. So any class, you can take that class and you can use this imify decorator. There are a few fields that you define that sort of tell you how you're supposed to represent that class to an LLM. And then when you add that decorator to the class, instances of that class have transform and query methods. And so you can say db.transform or db.query, or here m.transform and m.query on db. And you can, the transform operation is just a mutation to that object. And then the query method, so you can think of transform as being of type, tau to tau, right, for database to database. And then this query thing is like tau to s, or database to anything. So here we're saying update the table, and that will give us a new database with the updated table. And then query what were the sales, and the result of that will be a number, in this case 1250. The way that this works underneath, under the hood, is that the fields, the public fields of the, by default, the public fields of the class become data that you sort of represent to the LLM, and then each of the public methods, modulo some type signature checks and so on, become tools, right? And then you're basically doing tool calling against a sort of scaffolded version of your class. One of the things on our roadmap for next year is to go through a bunch of popular Python libraries and build out sort of custom MFI templates for each model family for those packages. Which brings us to the next topic. By the way, I stopped my slides halfway through because of the technical error. Do you know? We go 90 minutes, and we started at 3:30.
You have another 30 minutes.
Another 30 minutes. Perfect. Okay, great. So one of the things that Mellea is designed to support is what we're calling model inference co-design. The basic idea is that you modify your model weights in some way, right, by tuning. And then when you modify those model weights, you're also going to change things in your inference stack, right? So a few canonical examples of this. If you tune a model to do tool calling, you're probably going to introduce some specific syntax for doing tool calling, and so you need to modify your inference stack to do tool calling. If you modify your model to have like reasoning trajectories with some sort of think tag, well, I just said it, like you added the think tag, and so now you're going to have to like, you're going to have to modify the software around the model to be able to handle that reasoning tag and do the right thing with it. Constrained decoding is another example where in theory, right, constrained decoding, and in practice, right, you can do constrained decoding on any off-the-shelf model. In practice, often you like tune the model to be really good at generating JSON because you know that the constrained decoding against the PyData model is going to be a thing that you want to be good at, right? And so in some cases, the inference stack is changing while the model changes because you added new model features. In other cases, it's like the same old model feature, right? Of course, I can just like read off logits and constrain them by a grammar, but I know that people are going to want to do that with respect to a particular type of grammar. And so without changing anything in the inference stack per se, because that feature already exists, I'm going to modify the model weights, right? I'm going to tune to be really good at generating off of pydantic schemas, for example. So we think that this is it's not the future, it's here today, right? And one of the things that's happening right now is that if you hit OpenAI or Anthropic's endpoints, especially with their latest models, but this has been true for a while, you're not like hitting, like here's what is not happening. They are not taking your string, tokenizing it, shoving those tokens into a set of model weights, getting tokens out of the model, turning those tokens into strings and giving you that string, right? There's a whole bunch of software happening on both ends of that inference call. For most of these closed source model providers. That software stack is co-designed with the model, right? That infrastructure for doing that doesn't really exist in the open source community. And so the whole open ecosystem right now is operating with like a hand tied behind our backs, because when people run these evaluations, they run them on our raw model. When we release an open weight granite model, those evaluations get run against our raw model weights. And then we get compared to OpenAI or Anthropic doing who knows what behind that API endpoint, right? So that's a place where we want to try to help the open weight ecosystem sort of coalesce around, okay, how do you, if you do this model inference co-design thing, how do you service that to the end developer? So we're developing one way of doing that in Mellea. I don't know if it's what's going to stick, but we're exploring one point in the design space, and we hope that will inspire other people to do other experiments, find other points in the design space, and hopefully one of them sticks. Because we're really all in on this open weight thing. So that said, right, I'm going to speak specifically to you, and most of you, maybe all of you are not doing pre-training, you're not releasing sort of foundation models. Is anybody here on a pre-training team? No, okay, great. So you know, that's an important use case. It's something we're trying to support in Mellea, but modifying your model weights is something that anybody can and sometimes might need to do. There are a few reasons for that, right? One is that you need to add special knowledge to your model. So you know, we have a bunch of use cases like this where like, you know, you have some proprietary ERP system which has a bunch of data in it that just like isn't on the public internet, right? Isn't in the pre-training sets and is specific enough that like the normal universal priors of natural language are not helpful for sort of inferring in a zero-shot or few-shot way, right? You just need to do training. Process modeling is a sort of special case of that, right? So if you have special data, typically you also have process data related to those data sets, right? If you have some crufty IT system that isn't really documented on the public internet, you probably have lots of examples of traces of support tickets or debugging sessions or whatever related to that system, for example. And then the third reason is that you have you have a task that is sort of addressable using an off-the-shelf model, either in a zero-shot or a few-shot way. But you really care about getting an accurate, calibrated fault model. So you don't just want a YOLO answer, you want an answer with like some sort of confidence interval around it. This is something that you can train a model to do. If the model can sort of do the task, then you can build a data set that does the calibration thing, and you can get a model that is calibrated in some sense, but it's not going to be off the shelf. So these are 3 reasons why you might want to customize models. There are many others. We're just going to focus on the simplest case, which is I have some data that's not on the internet, need to tune because can't do it few-shot. So in the tutorial, by the way, this part is not in the Jupyter slides because like we can't on Colab we can't tune a whole model in a 1-hour session, but the code is in our tutorial, and you can run it yourself with like a few dollars on any you know or a local machine that's beefy enough. So this is a use case that's like sort of, well, the data's made up anyways. So we're just imagining that we have some manufacturer. The manufacturer manufactures a bunch of things. They have a huge data set of like customer saying like, here's a thing that happened, and then label, which is basically like a root cause analysis, right? And like all of this is like intentionally made up stuff. Like stem vaults are not a thing. They don't have RPMs, right? Whatever. So let's say we have a huge data set of this sort of thing. Mellea, when you install it, comes with a command line utility. One of those utilities, one of those the subcommands of that utility is an LoRa command. If you don't know what LoRa is, it's a way of tuning a model by only changing some of the weights, right? And so you can just think of this as tuning it's like a cheap version of tuning your model. Let's just think about it at that level of abstraction. And I'll get to what the A means in a second. So anyways, there's a subcommand that allows you to just do SFT on a data set. And then what you get back out is a checkpoint file that you can then use from Mellea. All right, so you can feed your data in, you get a checkpoint file. And then, and one of the things that you do when you run this command is you specify you specify the sort of format that you want the input and output to be expected in, And then based on that format, you can then use this train checkpoint in various ways inside of Mellea. And one of those ways is that you can use it as a requirement checker. So you can, for example, you can tune a model, you can tune a LoRa adapter on your data set, and then you can say, I would like at some point to check that that you use that set of model weights to identify the failing part, and be able to say a failing part was actually identified. Okay, so that command line utility, which you can go and use today, gives you a sort of like specialization in the small thing, right? You can tune a model, you can take that model, you can load the model weights, you can use it in various ways inside of Mellea. For example, you can say, instead of writing a custom function, I want to use a LoRa adapter to check this particular type of requirement. I want to use this LoRa adapter for my process reward model, etc. Right? So if you do that once, like it's like a reasonable thing to do. This is a thing people do, right? If you do it a whole bunch of times, right, you're back to one of these coordination problems. This time not with other humans. This time just like with yourself. You have like dozens of checkpoints sitting around. Each of those is like a big thing that needs to move in and out of VRAM at the right time. And there are serious costs associated with that, right? You don't want to host a huge number of specialized models. That gets expensive, either in terms of cost or in terms of latency or both. So for that reason, people often use these adapters. You can keep a single base model and swap out these adapters. The unfortunate thing about using adapters is that each time you switch out the adapter that you're using, you need to re-prefill all of the context. And so, for example, if you use an adapter to do a requirement check, you have to like rerun all of the context that you're going to do that requirement check on, which can get quite expensive. In these didactic examples, we have like dozens of tokens, but if you imagine there being like a whole PDF in your context or something like that, right? Then this can get quite annoying that you have to constantly redo this prefill step, and can have serious implications for the runtime of these systems. So the reason for the A in front of the LoRa in the Mellea train command is that what we're training is not a vanilla LoRa, but something that's called an activated LoRa. And the details don't really matter. The important point is when you take a LoRa and you use that LoRa on a model, you have to do that prefill thing. The activated models are trained in a different way such that you can take those model weights, load them, and then you use the KV cache that you already computed for the initial prefill, right? So you can use a base model. From that base model, you can generate. And then if you want to do a requirement check on what you just generated, you can load an activated LoRa, perform that check for the cost of generating exactly one token, no additional prefill, right? And you can swap out many of those LoRas, have one for each specific type of requirement, have one for a process reward model, have one for generating a particular type of thing, like choosing which tool to use or filling the arguments for a particularly gnarly type of tool. So you can do this nice thing where you just like train a whole bunch of customized models that are really, really good at one specific task. And then instead of having to like do the very, very, like from experience, very, 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 very painful thing of trying to figure out how to build one model that mixes all of that data in a way that gives you decent performance on all of those things and doesn't like degrade one of them too much, right? And running all of the experiments required for that, you can just say, like I'm just gonna like train LoRas for each of these specific things. I don't care if I like nuke the quality of that model for some other task because I know that I'm only gonna be using it for this one task. And it's effectively free, right? You just have the cost of reloading these LoRas, and even that, we have a whole set of work streams that we're planning on working with on our backends that allow you to basically treat that as much like one model as possible. Okay, that was a lot. Does anybody want to ask questions about that stuff? Okay. Yeah.
Sort of, yeah. I mean, maybe you can explain a little bit. I mean, I don't know if this is like diving too deep in it, but I don't know if this is gonna like time, but like, could you explain a little bit of how that works? Because I feel like, yeah, my understanding of LoRa is it sort of adds its change to the weights as is. How does how does this activated LoRa work differently from just a general LoRa adapter?
So that's pretty similar. You're just like, there are some of the weights that change,
Yeah.
and the rest, most of them mostly stay the same. If the trick with activated LoRa's is when you train it in such a way that it's principled to reuse the existing KV cache.
Oh, okay. Oh, so this is happening at the training.
It's happening at the training. At training, and you train in such a way that you can reuse the KV cache of the base model.
Okay. Okay. So it's it's like not a LoRa adapter. It's a LoRa.
It's an a LoRa.
Okay. Gotcha. Okay.
If you sat down with a pencil and a notebook and know what it looks like on pencil and paper to define a LoRa adapter in the training process for it, and then you say, what if I reuse the KV cache of the base model? How does this change? You could probably rederive. Which is just to say there's no secret sauce. It's like, that's the observation. I want to reuse the base model KV cache, not have to reprefill. Once you know that that's like the thing that you want to do, like, it's like the obvious thing. Okay, I got an excellent foreshadowing question about the next section of this, which is a case study on that big prompt that I showed at the very beginning, right? So I was talking about how horrible these prompts are. So this is an actual prompt. This was used as an example, but also is actually it's a GPT researcher style prompt taken from this GitHub repo. So we took this just as an example that we could share sort of in the open, talk about as openly as we like. We just re-implemented this mini researcher prompt as a Mellea program. So this lives in our GitHub repo. It's fairly small. You can just go read the code. And in fact, in the future, I might do exactly what you were asking, which is just grab the code and go through it line by line. I'm not quite going to do that. I'll do a little bit of it, but I'll do it pictorially first, right? So here's an example of a prompt that you might give one of these researcher-style agents if anybody hasn't seen one of these before. It's designed so that you can ask things like, how does a recent acquisition affect IBM's earning outlook? Or whatever. You're just asking for a research report, right? The details of what you're asking for, these prompts are designed to be generic, right? So the details don't particularly matter. And then what these prompts do is like they find, if you read this long prompt, right, what you'll see is that basically what it's doing is getting a bunch of documents and then doing a bunch of things that you would do with that document if you were to write a research report, right? So first you check that each of the documents is safe for work, and then you summarize each of the documents, and then based upon those summaries, you create an outline for a research report, and then you go through that outline and you systematically write the report based upon your outline, right? High school English. So what we do in Mellea, instead of writing one giant prompt and then feeding the documents into that one giant prompt, we just have a sequence of much smaller prompts. So for each document, we pass that document into a model, and we say, is this document safe for work? The model that we pass it in here is not a base model. It is an LoRa that was trained on the same data set as Granite's Guardian models, which are sort of safety checking models, right? So we feed the models all into these Guardian checks, and that tells us whether these documents are safe for work. We're using a model that's been specifically designed for that, that's been sort of robustly evaluated on a whole bunch of safety metrics, instead of just using whatever base model we happen to be using for the rest of the model. We then take each of those same documents, we ask for summaries against a base model, and then we, based upon each of these, right? This is not one big call asking us to summarize all the documents. This is a sequence of smaller calls that can be parallelized. So we can drive our time to first token down pretty significantly by doing that, and then we create an outline, and then based upon the outline and the summaries of the documents, we generate our report. So again, a couple of points I'll just reiterate now, but we've said several times now, right? If you have a very long program that you've written in natural language or a prompt essay, if you want to change anything about that, you have to change everything about that, right? The natural language program is this big totally entangled thing. If you change one portion of that, it might change the behavior of some other part of the system. And this is not theoretical. This happens all the time. Conversely, for the Mellea program, right, if you want to go into any of these individual steps and change the behavior of those steps, no problem, right? And so, for example, if you find that your outlines are pretty lacking, like I get great summaries of my documents, but the outlines are kind of bad, you can go into that step and you can really hyper-optimize. You can create a separate whole workflow for that, or tune a model for that, or anything else. Similarly, at the document step, if you find your documents are very big, you can, like, for example, pass them into dockling and then sort of subdivide them into sections, figure out which if you know the type of report that you're writing, grab particular sections from like a tax document, for example. So the point is just when you do this decomposition thing, you're not doing any more or less work than you would do with the prompt essay. You're already writing out in natural language all the steps you wanted to do anyways. It's like basically the same amount of work to just do that directly in a programming language. But by doing that, you have each of these steps isolated. Right? Here's a little snippet of sort of top-level code. It is as simple as I've made it out to be. So you first check that the input is safe, check that the document is safe, and then you summarize each of the documents, and then you generate an outline, and then you merge all of that for the generation of the final report. We can step into one of these. So if we look at the summarize document step, again, like it's pretty much as simple as it sounds. You provide an instruction that says, please summarize, and then you pass a requirement saying like the summary ought to actually be a summary. So in this case, we say, can this be 3 sentences? And you could take that requirement and even like just do that check deterministically, right? Either check counting, say a maximum amount of characters, or like try to, just directly parse the number of sentences in the text, or just use the LLM. We have a whole bunch of other worked examples in our GitHub repo. So we have the mini researcher thing. We have some examples of what classical agent implementations look like when you implement them as Mellea programs. We have some RAG examples. We have some VLM examples. And this is sort of growing all the time. OK, so to summarize, right, Mellea is a library for writing what we call generative programs, which is just this different way of building applications that use LLMs or agents, if you want to call them that. The library is designed to enable you to write robust and composable programs that hide information where it's needed, that provide high-level interfaces that other people can use. We've designed Mellea to work well with local inference on small models, because when you program in this style, you can use small models to do big model things, right? So one of the things I should have said about the researcher thing, to run the researcher prompt, you typically need like a fairly large model. To run the Mellea program, you can run like very, very small models on your laptop and get similar or even better performance out of that researcher functionality. Although we've built it for local first models, it's also ready to scale. So we have support for OpenAI style backends, and there are various teams working on deeper VLM plugin integrations for various things, including ALORAs. And the whole thing is licensed open and permissively, so it's all licensed under Apache 2. And our plan and goal is to continue working in the open alongside the open weight development that our Granite series team is doing with the foundation models themselves. There's a long-form tutorial GitHub repository, and you can install from PyPy with pip or UV. OK, so that's Mellea. I think I've left plenty of time for questions, comments, or just chatting. Thanks for your attention. Oh yeah, and let's do the mic thing. Yeah.
Yeah, I just had one more question. Is there a case, or are there cases where you'd be using like different sessions across like one application, or do you generally just use one session?
Yeah, so there are two reasons why you might use multiple sessions. Remember, a session is a combination of a backend and a mutable ref to a immutable context. So those are the two things, right? You might have multiple backends that you want to use, and so you instantiate multiple sessions. Or you might want to be using the same model and the same backend the whole time, but you have like multiple pieces, multiple like representations of context that you want to keep around. And you can do both of those things. The caveat is like if you're using local, models, you've got like a little bit of a weight loading coordination problem there if you want to use like a llama model and a granite model at the same time, like, you know, you're going to be swapping out the weights. But if you're hitting like an inference endpoint, right, you can just use two sessions, commingle them.
On the prior slide, you mentioned something about image models, or what was that?
Oh yeah, vision language models. So these are models where you can provide images as input.
Okay.
So the image just gets tokenized like you would tokenize text, and then you can ask a question about a graph or something, for example.
Actually, I do have a question as well.
Yeah.
So it doesn't. So if I understand right, this is not like necessarily like fall into the definition of an agent, right? Because it's not really making decisions. It's more like workflows. Or am I misunderstanding something about it? I guess like depends on your definition.
Yeah, I mean, So the terms are undefined, right? So, but okay, so the reason that we use the term generative programming is because we wanted a word that wasn't agent, that just meant like a program that calls an LLM. So agents and workflows are both instances of generative programs. There are many other types of generative programs. There are inference scaling being like another third obvious example. So you can write agents in Mellea, and if you use sort of, and you can write agents and agent frameworks too. The sort of like Melleic observation is that the primary problem with pure agent implementations is that you have that outer loop that's doing like a non-deterministic choice over a big set of stuff. And when you do a non-deterministic choice over a big set of stuff, that is like inherently a combinatorial thing. And that's why like the fact that like that number is that number where things break down in the length of the trajectory is like between like 11 and 15, right? Take an exponential function and make it big enough that your computations start getting intractable, and it's gonna be like the exponent is like in that range, right? And this is not a coincidence, right? You're doing a combinatorial thing there, right? And so by doing this like constrained choice over your non-deterministic set, using preconditions and postconditions of each process, you can sort of substantially reduce the size of that search space. It's like constrained search is easier than unconstrained search, you know, in a discrete space.
Thanks. No, yeah, that's useful.
Cool. All right, well, Jake and I will be around, and Mellea is our full-time job until they tell us that it can't be, which is hopefully never. So if you have, you know, if you see things that you want, encounter bugs, whatever, just feel free to open issues on our issue tracker. We'd love to hear from people who are playing around with this. All right, thanks everyone.